Greetings once again from Rescue Shuttle Control. You've made tremendous progress over the last several sessions, and we are now in a position where we can pull together a lot of the work that we've been doing and really start to add features to our security system. Today, our goal is going to be to take what we did last time, which was our security password system that operated through the keyboard and the serial monitor, and add to it the capabilities of both light output and sound output that we've been developing in some of our previous sessions. In order to do that, it means that we're going to have to make some modifications both to the hardware and to the software, although you'll see that much of it will be familiar to us because it will just be slight modifications over what we've done so far. Let's start by taking a look at the breadboard and the hardware configuration. As we examine the breadboard as it's connected to our Hero and also the keypad, things should look pretty familiar. In fact, we're going to be using the buzzer, the passive buzzer, in pretty much exactly the same way that we were using it very recently. Similarly, we'll also be controlling the RGB, the red, green, blue color LED through outputs coming from the Hero as well. The only thing that's really different here is we've needed to rearrange the layout a little bit. It turns out that as we add more and more functionality to our system here, real estate on the pins of the Hero is getting harder and harder to come by. And so we need to move things around just a little bit. In particular, one reason why we need to move things around a little bit has to do with the color LED. As you'll remember from some of our previous discussions, the way that we control the brightness and the color shade coming from the LED is using pulse width modulation. That means that the digital outputs that come from the Hero can be set to be on or off for varying lengths of time. So for example, if we activate one of those pulse width modulated output pins with a value of 255, that means that it's on all the time at the plus 5 volts. If, on the other hand, we turn it on with a value of 128, then it's on half the time, a duty cycle 50% on, 50% off. And any value between 0 and 255 will give us a proportional relative amount of time that the LED is on. Now, the reason for bringing that up is that not all the pins on the Hero are capable of doing pulse width modulation. We may have mentioned this previously, but if you look carefully at the Hero board, and you may not be able to see it on the video, but you can examine it on your own Hero, only some of the pins have a little tilde mark next to them. It is only the pins that have a little tilde next to the number that are pulse width modulated. In our case here, 3, 5, 6 are eligible, 9, 10, 11 are also eligible. Now, unfortunately, the way we had previously configured our keyboard setup, we'd used up pins 9 and 10, which were being used to control some of the columns on our keyboard. But we need those pins 9 and 10 to be used to control the LEDs. So for that reason, we've relocated the columns corresponding to pins 9 and 10 upward to pins 12 and 13. And so there's a little split off here in our ribbon cable. Those top two lines corresponding to the top two column outputs on our keyboard have just been moved up a little bit to make space for 10, 11, for 9, 10, and 11 to correspond to blue, green, and red, respectively. We've also made a little room here Previously, I think we were using pin 10 to send a signal to our buzzer. 10 is now busy, and so we've relocated that with this orange wire to pin number 8. So the principles used here are the same. We just rearranged things just a little bit. But we should have what looks to you like a familiar circuit for driving the buzzer and for driving the LED with red, green, and blue signals. All right, so everything else should be familiar to you from our recent project sessions. The next thing we're going to do now is look at the code that we've modified slightly in order to take advantage of this now new light output and sound output capability. Most of the code will look very familiar to you from our last session, but we'll just walk through it briefly to highlight some of the changes and allow you a chance to think about what they mean. At the top, you can see that we've naturally had to introduce a few new variables corresponding to our sound and light output. So we have a new integer variable, which is buzzer, set to 8, because you'll remember we're now using pin 8 as our output for the buzzer. And we've assigned pins 9, 10, and 11 to blue, green, and red, given them the names red pin, green pin, and blue pin, corresponding to the new assignments that we just discussed on the board. Our row and column assignments for the keyboard have not changed, so we don't need to spend too much time on that. And we're going to stick with a password length of 4 characters with an initial default password of 0000, which you'll remember is just exactly the way we programmed it last time. Also, as last time, we'll have the same keypad character assignments of the numbers 1 through 9 and 0, A, B, C, D, star, and pound assigned as before to our keypad. You'll notice that we did have to change the pin assignments corresponding to columns because of the relocation of the pins that we needed to make. So whereas before our column pins used to be 6, 7, 8, and 9, now they're 6, 7, 12, and 13. We've just reassigned those 2 moved column pins. Otherwise, everything should be just as before. As before, we define a custom keypad object. In this case, we decided to name the keypad security pad just to change things up a little bit. So we'll now refer to it by that name, security pad. And we can go ahead now and examine the functions, both our custom functions and our setup and loop functions, to see how we're taking advantage of this new capability. Just as before, we have a custom function that's the unlock mode function, and you'll remember that its purpose is to handle attempts by the user to enter a password and report back either success or failure depending upon the results of the key inputs. We've added to that a few new features. You'll notice that at the beginning of unlock mode, we begin by shutting the LED off completely from whatever state it was in before unlock mode was called. So it may have been showing some color before, but now it's set to 0. Then, as before, we prompt the user to type in a password. And after a short wait, we begin our loop. This is the while loop that does nothing until a keystroke is detected. So this while loop will continually repeat until result is something other than 0. When result is something other than 0, then we drop out of the while loop. And since in this case, what we're doing is we are checking a password, we take result and we compare it with the first time through the first character in current password. And as I goes 0, 1, 2, 3, we'll successively check whether or not result matches the corresponding character in the current saved password. If, as before, the result does not match, this test will cause the serial monitor to tell the user you've given a wrong password. In addition to that, we're now going to play a sound. The sound will be played by this custom function called play error, and we'll see in a few minutes what play error does. Once we've done that, once we've notified the user on the serial monitor and played the error sound, we then return with a code of -1, remembering that a code of -1 tells the loop function that this failed. So that's what happens if a pressed key does not match what's expected in the password. On the other hand, if it does match what's expected, we give the user a little feedback. As before, we type a star in the serial monitor just to show that a successful key press was made. And in addition, we'll play a little sound, a little beep with play input that will give the user a little audio feedback as to the successful key press. And we'll also give some visual feedback by flashing the LED blue for just 1/10 of a second. So there'll be a little brief blue flash that gives feedback that says that was a good key press. After 1/10 of a second, we turn it back off, and we are done with this loop, which will go through 4 times for the 4 characters of the password. And if we have made no mistakes during that process, then we'll drop down and hit the serial message, which just basically says you were successful, you unlocked the device, and we play a success tone, returning with a value 0, which is a signal to the calling function that says that this was a success. So, very familiar or very similar to our previous version of unlock mode, but now with just a few new audio and visual features to add to the functionality. All right, with that, let's explain some of these new functions that we just introduced. The sound functions that we just saw are play success, play error, and play input. And based on our previous experience with the buzzer, these should be pretty easy to understand. In the case of play success, what we do is we play a short tone for 2/10 of a second with a sort of a low pitch of 1000 hertz, and then a longer tone for about 1 second at 2700 hertz. The idea here is to make a little sound that sounds something like ta-da, a low and a high. You can change that if you think it doesn't sound very good and want to change it to a better success sound than that. Play error gives a sound of its own with a frequency of 147, so that would sound like a low-pitched buzz, sort of a eh type of noise. So that should play for 1/10 of a second, and that's what happens when we call play error. And finally, the feedback tone from just pressing a single correct key is just a very brief 50 millisecond beep at a frequency of 880 hertz. So that should just sound like a very brief beep. So those are our 3 sound functions, pretty easy to understand. We also have a custom function to light the LED, and this is just the same as the one that we used a few projects ago, a few sessions ago. It's just our Rgb Color Function that does an analog write to the red pin, the green pin, and the blue pin, corresponding to the 3 values that are entered when we call Rgb Color. So that should be review for you and pretty straightforward to understand. All right, so that's it for our external functions. And so now we can look at setup and loop, and we should be pretty much complete in terms of an understanding of what's going to be happening here. Setup, since we're now using the LED, needs to call pin mode to set red pin, green pin, and blue pin to be outputs on the hero. So that's familiar, and we know how to do that. Just as a little signature or a little signal to the user that setup is occurring, we've decided to let the LED display white. That's 125, 125, 125. So display a white color for 2 seconds just to indicate startup is going, and then shut it back off again until further instructions. Then we do just as we did during our last session. We set up the serial monitor, wait a couple seconds, and then print out a prompt on the serial monitor asking the user to either press star to reset the password or to press pound in order to access the system using the present password. So that should be fairly familiar. And so now we'll take a look at the meat of the loop code and see what's changed or what's different there. Not too much is different. Again, all we're really doing is adding a few new features to what we did in our previous session. So you'll see here that just as before, we're going to call getKey on our keypad, on security pad. So we call getKey. The result then can be any one of the characters that we've pressed on the pad. If we've pressed the star character, then we call unlock mode, and that's basically going to first ask the user to enter the current password before they are allowed to change the password. If that returns -1, if that returns less than 0, then that unlock mode failed. And so that leads to a message that says access is denied, and we light the LED to red. 125.00 should give us a medium brightness red color. Otherwise, if the access value that's returned from unlock mode is non-negative, that means it was successful. And so we can go ahead, light the LED to a green color, wait a couple of seconds, turn it back off again, and then tell the user, okay, I'm ready to accept the new password that you want to enter. And at this point now, we do just as we've done before. We enter the while loop that waits for key input, and every time a key is pressed, we take the result of that key press and stuff it into the next available slot in current password, replacing the old password that was there before. As before, we'll print a star as feedback that the key was pressed, and not as before, but now that we have this new capability, we'll also play a little beep and flash a little blue light as each one of the 4 characters of the new password is entered. At the end of that, we turn the LED off, and after we've entered 4 of these characters successfully, report to the serial monitor the password has been successfully changed, and we turn the LED on to a steady green. So that basically is the result of what happens if the user types a star on the keypad. Now, the other possibility, so we have that up here, this is what if result was star. The other possibility down here is what if result was pound. If result was pound, then we're not going to be asking to change the password, we're just asking to enter using the current password. So we have a shorter block of code here. All we're going to do is call unlock mode, which will get either a successful or an unsuccessful password entry from the user. If it's unsuccessful, then we'll type password error, access denied, and light the LED to red. And if it is successful, that is, if access returns non-negative, then we print the welcome message, set the RGB LED to green, and we're done. So that is all of the possibilities of what can happen inside of our loop function. And that exhausts all of the new features that we've attempted to add to our to our code. So with that, I think it's about time for us to see if it works. So now that we've finished running through the code and understand all its new functionality, let's go ahead now and run it through its paces. Let's test it and see if it works as we've designed it to. If we look again at our breadboard and the hardware setup, we should verify that we have, in fact, hooked things up as expected by the code. You'll see that we do have the keypad connected through this ribbon cable to the appropriate pins, the newly revised pin setup on the Hero board, freeing up the necessary pulse width modulated pins that are connected to the red, green, and blue channels of the color LED. The first time that I set this up, I actually did make a mistake because it's quite easy to transpose some of those wires in the ribbon cable and get them hooked up in not quite the right order. The result of that mistake was that I was getting erroneous key presses when I would press a certain row and column. Another thing to watch out for is to not forget to include the current limiting resistors in the circuit to prevent sending too much current through the LED and burning it out. So we have those 200 ohm resistors in series with each one of the red, green, and blue channels here as we're driving the color LED. So without further ado, we should go ahead and upload our code to the Hero and see if it functions as we've intended it to. So we'll go ahead and verify our code here. Make sure it doesn't have any syntax errors in it. Looks like it's compiled successfully. So we'll go ahead and we'll upload it. And we'll be expecting when we upload it to see a white LED status light come on. That'll indicate that we've successfully begun the execution of the code. So we'll upload now. And as we watch the breadboard, we should expect to see a white light come on. There's our white light. Let's open up the serial port so that we can see the prompts that we're getting through the serial monitor. So we got the expected white status light on the LED, and we've got a prompt now from the serial monitor that indicates that we should press star if we want to set a new password, or we should press pound if we want to access the system using the existing password, which, as you'll remember, is set to an initial default of 0000. So let's go ahead and test the current password to make sure that it works. So we'll go ahead and we'll press the pound key, which is this one right here. And when we press the pound key, it says, okay, we can now enter a password to get in. That should be 0000. So you'll notice a few things right there. You'll notice that we did get the confirmation key beeps when we were pressing the key 0 for the password. Each one of those key presses was accompanied by a brief blue flash, as our code intended to. And finally, since we entered the correct password in, we got the da-da tone from the buzzer, and we got a green light indicating a successful unlock. Since we like to test our code completely, let's see what happens if we enter an incorrect password. So let's go back again, press pound once more to enter a new password or enter a password. Again, if I press 0, which it's expecting, I get a beep and a blue flash. But if I now press an unexpected character, something other than 0, like D, for example, I get the beep, the low-pitched beep, and a red. a red light. And you'll also notice on the serial monitor that we were informed that this is a wrong password and access is denied. So what we have now verified is that the options for entering passwords are successfully processed and respond appropriately. So the next thing we should check is our ability to change the password to a new value and then enter using that new password. So in order to do that, we'll go ahead and instead of pressing pound, we'll press star. So star, once again, gives me the unlock prompt. I need to know the initial password, which I know is 0, 0, 0, 0. I'm successfully in, and now the system is asking me to enter a new password. So I'll pick a new password. I'll choose the password 123A. So 1, 2, 3, A. Green light indicates that I've successfully entered the new password, and it should be in effect from this point forward. So let's go ahead and finally test that functionality as well. So if I now want to enter the system from scratch again, I'll go ahead and press pound once again. So pressing pound gives me the prompt to enter the password. If I forget that there's a new password and I try to use the old default password, it should fail. Let's see if that is in fact the case. 0 gives me a failed password entry. So I should now try using the new password. So once again, I'll press pound. And now I'll enter the new password. 1, 2, 3. Let's press C. Oh, no, that wasn't correct. Let's try it again. 1, 2, 3, A. Success, green light, and it appears as though we have successfully tested all the functionality that's built in to our keyboard security system. You may want to modify in some respects the code. You might want to work with different sounds or different light signals or different prompts from the serial monitor. And I invite you to do that as a way of practicing and further reinforcing what you've learned so far. But at this point, we have something very useful that we can now build on as we put together our system and make it capable of doing more useful functions. And so for now, remember, build everything and invent safe.